talk and move on now to the second talk of this session. The second talk is going to be presented by Hans Hübl. And Hans, many of you know, is one of the PIs of MCQST. He's also the Deputy Director of the Walter Meister Institute for the Bavarian Academy of Sciences. What fewer of you know is that he started his life with his PhD in the Schottky Institute back, I don't know, what was it, 2007 or so. And at that time he was working together with Martin Brandt on coherent manipulation of phosphorus in silicon. So it started off this topic. He then spent a couple of years in Australia, I think with Andrea Morello and conspirators working on similar types of topics before coming back about 10 years ago to Walter Meister Institute. And he kind of does everything. If you look on the Google Scholar page, he's working on the topic he's going to talk about today. That's nano-electromechanics. He's also worked on superconducting quantum circuits, lots of different things. So Hans, we're looking forward to your talk, and maybe you can take it away.
Yeah, thank you for this kind introduction, John. Can you hear me, and can you see my slides?
We can see your slides fine.
Okay,
I can see you
perfect.
as well.
So thank you for this kind introduction, and it's a pleasure to have the opportunity to present to you our recent work in the direction of how to inductively couple nano-electromechanical systems. The question that I want to pose for today is this actually a pathway towards strong coupling? And I actually should be more precise with this formulation. The question more goes into the direction of, is it a pathway to enable strong optomechanical vacuum coupling? And there is a difference, and I will talk about this during my talk, and I try to make the difference clear. But before going there, I want to acknowledge the funding agency. So you see here the logo of MCQST. So I thank very much the cluster for funding this fun enterprise that I will talk about today, as well as a European Fed Open project, which is called MaxSense. And before actually starting off, I want to kind of highlight the people who actually managed to do all this and to make it happen, to do this in the lab. This is Philipp Schmidt, who now moved to Markus Aspelmeier in Vienna, Stefan Pogozalek, who helped us with tunable microwave resonators, Mohammed Amavi, who actually fabricated these devices together with Philipp, who is now a PhD in the group of Friedemann Reinhardt, and Thomas Luschmann, who took this a bit over and pushes this now further on. So we are sitting here in the quantum sensing session, and therefore I would like to take the opportunity to take this step back and to kind of revisit what quantum sensing is. And I found a nice review of modern physics, where actually one of our moderators is an author of, together with Degen and Capellaro. And they state in the abstract that quantum sensing describes the use of a quantum system, quantum properties, or quantum phenomena to perform a measurement of a physical quantity. And I want to distract you now and kind of talk in particular about the mechanical properties that you could measure. And there I would say you can think of measuring forces, acceleration, masses, or displacement. So everything is well at the heart what you know from your classical mechanics undergrad lectures. So, and what we do, and where this is getting in the direction of quantum sensing, is we couple this to an optical resonator or microwave resonator. And what I want to kind of convince you today of is that this gives you benefits in the direction of signal-to-noise performance, that you have the opportunity to prepare quantum mechanical states, and that you can also consider aspects of information storage in the systems. But what is actually an optomechanical systems? And since the audience is quite broad, I want to review that a little bit. So what we talked about up to now is this element. So take this mirror, it has a mass, and this mass is connected via a spring to a rigid support. And so we all know that this mass together with the spring constant will kind of express harmonic oscillation with a characteristic frequency which is given by omega m. And this kind of blue double arrow should now depict that in this classical trajectory that you have a displacement, And there comes this kind of second mirror into play, which is kind of fixed in space. You form here an optical Fabry-Perot cavity in this example, and you modulate now with this displacement the length of this intermirror distance, or this kind of cavity length. And what happens now is that you're primarily monitoring the frequency of this optical cavity, which is now takes an information of the displacement in its frequency. So what happens is this mirror oscillates, this displacement oscillates, and via this coupling constant G, this displacement is translated into a resonance frequency shift. And this is what we will talk about. You see that this is an extremely general concept, and therefore there's no wonder, so to say, that you can implement this, this strategy in a lot of systems ranging from atom optics to the LIGO experiment to nanostructured photonic circuits to superconducting microwave circuits. And I want to kind of explore with you today these superconducting microwave circuits for this purpose. To give you a kind of more full picture, so this is the Hamiltonian describing the entire process. We have our optical cavity here, we have our mechanical harmonic oscillator, and we have this interaction term, which is something like the displacement here in B dagger plus B. And then you have this coupling constant G naught here, which is now renormalized by the 0-point fluctuation. So what can you do with these systems? And this is actually an interesting question. Typically what you would say is, yes, these G naughts, they are small. This is a pity, so to say, but not a major road stopper, because you can try to linearize this Hamiltonian, this interaction Hamiltonian. And if you do so, you end up basically with a system which is a beam splitter Hamiltonian or a squeezer Hamiltonian. And what you see here in the prefactor is that this is why I say it's not a major roadblock. You can now boost your intrinsic coupling with the square root of the photon number that you use for probing the system. And this is an extremely successful and fruitful field. And people could demonstrate ground state cooling, excitation of mechanics, storage of microwave excitations in mechanical systems. People think about non-reciprocal devices, squeezing, induced transparency effect, and this is all kind of based on the assumption that you can reach something in the direction of this strong coupling regime. And here, the strong coupling, and this is what I kind of highlighted on my title slide, this is you need to achieve here that this G naught times boosted by the photon number is larger than the mechanical frequency. That's normally a piece of cake. And then the line width of your optical system or your microwave resonator, this is actually the hard thing to do. You can then say, or get the standpoint and say, okay, but this is only a linearization of this interaction Hamiltonian. What can we do if we get the full deal, so to say? And what you want to achieve in this range is that you actually outperform with your G naught the mechanical line widths and the kappa. The mechanical line width is not the problem again. The kappa is the hard challenge. And if you can do that, then you can basically access this full portfolio of this nonlinear interaction. You can prepare mechanical quantum states with negative Wigner functions, where you can do experiments where you have single phonon, single photon blockade, or you can think about generation of non-classical lights. So this is what the aim is for, what you can achieve if you boost this coupling. And actually the main part of my talk is to discuss with you what kind of handles do you have in superconducting systems to push this. Okay, let me introduce the contestants to you, or the ingredients that you need. So I talked about this general concept of an optical cavity in the terms of a Fabry-Perot cavity. We are not using optical cavities, we're using microwave resonators, and you can imagine them as a basically planarized version of a coax line with where the center line is split at 2 points where some pieces are missing, and then you have a standing wave pattern between these, so to say, mirrors here, building up your optical cavity, or it looks like an optical cavity. To give you an impression how this looks in real life, you take, or we like to take coplanar waveguide resonators. Coplanar means that there you have a center line surrounded by ground planes, and this center line is designed to have a certain length to match our frequency requirements. And at the end of this center line, there is our mechanical aspect of the device. We couple these two feed lines, microwave feed lines, in order to perform microwave spectroscopies. So what is the second part? The second part is basically a miniaturized guitar string. So if you take your guitar at home, you can convince yourself that the frequency which comes out is in the kilohertz range. That is what you can do in an audible concept. This scales with the length of the guitar strings if you take the stress, the tensile stress, and the density fixed. And this is actually what we do. We scale this down to a string length of roughly 20 microns, 30 microns, some of this sort. And this gives us megahertz frequencies. But conceptually, this is the same. So now you can ask, what are the roadblocks? What are the hurdles that you want to overcome if you want to drive or push this optomechanical couple strings? So keep in mind, we are still kind of conceptualized in this Fabio-Perot cavity. We have the displacement, which translates to the eigenfrequency. So this coupling constant is basically given by the frequency change with the displacement. And for a capacitive coupling in a circuit type of environment, you can easily write down a element equivalent circuit. You have here your inductor, your capacitor, and now you basically implement a capacitance which is mechanically compliant, which kind of translates displacement into capacitance. And a superb example for this is what I took here from John Teufel's work. There are many similar devices around in the wild, but I think this summarizes the performance pretty much. You have here the inductor, this coil type structure, and you have here the capacitance. And so it's obvious that you need to kind of get a large capacitive change CG compared to C in order to boost your optomechanical coupling. And this is what actually the group did. You have here this drum type resonator, which looks, if you make a cut through this thing like this, you have a ground electrode, you have a top electrode. By manufacturing, you get this separation between of the electrons in the order of 50 nanometers. These drums have 0-point fluctuations of about 4 femtometers, and then you're basically there. You can basically just plug in your values here, assuming a planar capacitance model, and then you get a coupling rate of 300 hertz. You can calculate that back of the envelope, and that's what actually these groups see. And this is the kind of one of the prime examples how you can push this coupling G0. And the question is, can you do better than that? And the answer, or what I want to convince you, is that you can evidently or try. And the alternative coupling scheme that you can go for is this inductive coupling. And what you need to find is a circuit element where the displacement can be translated to an inductance, and then you do basically the same thing. That's the conceptual idea. And I think this idea is decently established in the meanwhile. So there was seminal work by the Itaki in the Harry van der Zand group some years back. The theoreticians picked up on this and said, yeah, this DC version of the SQUID, it's a DC readout here, can be easily kind of expanded by coupling this to a microwave resonator. And then there's a little bit of an experimental gap of 10 years, as you see. And then besides us, 3 other groups managed to actually create devices which can do that. Okay, so what is the device idea? You have here your coplanar waveguide resonator. You shunt this coplanar waveguide resonator with a DC squid to ground. This is the workhorse of Josephson parametric amplifiers, so to say. And the idea is that this DC squid, the superconducting quantum interference device, can be represented by inductance. And the inductance is given by the flux which is in this loop. So what you do basically is you can tune this inductance by an external magnetic field which is perpendicular to the structure. And if you're freely suspended with this kind of string that is free to vibrate, there is also displacement which changes this flux, which changes the area. And this is also translated into an inductance change and hence in the frequency change. You can go through this derivation again, and then you find that this optomechanical coupling constant G0 is scales with the slope of this frequency tunable microwave resonator with an external magnetic field, the length of the string, and the 0-point fluctuation. And the last part here that's pretty easy to understand. This is basically the flux that you see here in terms of 0-point fluctuations, the green area. And the front here has something to do with the slope of these frequency tuning curves. The frequency tuning curves looks basically like this here in the lower right diagram. You get this characteristic lobes because here you increase the inductance, that brings the frequency down and then up and down and up. So you have here the flux periodicity, and you can utilize this. You can see it immediately that you tune the coupling from off to on. And the question is now, can we achieve a strong vacuum coupling? It's also nice that this could have the potential to see second order couplings in the optomechanics, which is interesting for phonon number measurements. And there's the benefit that you could think about using this structure or the tunability of the structure in terms of either amplification schemes or modulating the coupling. So this is our device. We talked about it already. This is the coplanar waveguide resonator. It's shunted now with this squid. And you see the squid in an angled SEM here, where we have here 2 Josephson junctions, here 2 clamping pads, and here 2 strings which are freely suspended, hovering above the silicon surface. And this is what we will look about. We will do microwave spectroscopy. We use sometimes the trick that we have a piezo actuator shaking the sample to actually create large amplitude motion here to make everything easier visible. And this is basically the main technical aspect. Keep in mind, we have 2 strings. These 2 strings have in-plane and out-of-plane modes each. So we see roughly something like 4 modes, and I will kind of select the modes accordingly, depending on if I apply the field perpendicular to the surface or in plane to the surface. So the orientation of this external magnetic field matters. What we do is we do everything in microwave spectroscopy. So we send microwave signals in, they go through the sample, interact with the sample, interact with the mechanics, and then we analyze this carefully. And I will kind of spend a few words when I change this environment or this setup here. Okay, so what's our microwave resonator doing? So here we have flux against the transmission of the device under test of our optomechanical device. We see here a microwave resonator as an absorption dip in darker blue. They have this lobe type structure, which I told you about. And from this lobe, you can basically check the flux periodicity. So this is a measure of field calibration. And from these lobes, you can extract information about the squid that you have actually manufactured. You can directly read out of this by taking the numerical derivative that here there's basically no slope, then you have here strong slope, so this is done for you here. And we see something like 10 gigahertz per phi naught slopes, so this is ballpark. You can analyze the line width of this microwave resonator, and it sure goes up with increasing slopes. And I gave you here for reference the mechanical frequency that we will see later on. So we can operate this device for a kind of large range of parameters in the so-called resolved sideband regime. Okay, let's look into the thermal displacement. This is the one of the versions how you can actually quantify this optomechanical coupling constant G0. So what you do here is you basically have a tone in a Raman type system interacting with the mechanics. So you can either excite phonons and then get photons out which are of lower frequency, or you can annihilate phonons and then you get photons out with higher frequency. So these are the options we chose here for this configuration because this is a bit advantageous in kind of detection efficiency because the scattered light is going into the cavity. We can measure here this thermal displacement noise spectrum. We see our mechanical frequency with a line width of about 30 Hertz, which is pretty decent. It's a Q factor of around about 200,000. And using this calibration tone technique, which is kind of established, we can convince ourselves that we have here coupling strengths of G0 of 1.6 kilohertz. And you have to take this in comparison to the 300 Hertz that I've showed to you. So we have here already a boost of roughly a factor of 5. This is also, and I want to mention this, read out with a coherent tone which corresponds to on average a photon number of 1.6. So it's extremely low power levels that we use in order to create this or measure the thermal sidebands. Okay, you have to take care about this in this situation. There is no heating as we convinced ourselves, or minimal heating. We see that these strings have atto-Newton per square root of its first sensitivity, which is somehow expected from these strings, but now we can read that out with femtowatt powers. Okay, I told you that you need now, or that you can tune this coupling, and one of the tuning parameters is the slope or the of the microwave resonator tuning here. So you see basically here these lobes again, and we used them several working points in order to convince ourselves that this G0 scales with this slope here. And then the other tuning parameter that we have is the external magnetic field. So you can basically wander out several of these lobes, get more external field, and then boost your effective coupling rate. Both of them, you expect a linear relation as function of this slope and a linear relation of the external magnetic field. And we measured this. So the red data points are these thermal noise data that I showed to you. And using, with the help of our piezo actuation drive, we can fill in the gaps basically and convince ourselves that there is indeed a linear relation. So 1.6 kilohertz, that's far off what I actually wanted to show to you. However, you can basically play the mind game and think about going from an out-of-plane field configuration to an in-plane field configuration. And therefore, this quantity, this figure of merit comes handy. So just take the scaling of the optomechanical coupling constant with magnetic field. So this is roughly for this device 3.1 megahertz per Tesla. And if you would kind of just plug in the numbers, take the critical field, the BC2 of aluminium of this layer thickness, it's about 70 millitesla, then you already should be at 200 kilohertz, which is dramatically large for this business. So we think that this should, or is promising that this gets within reach. We should kind of need to basically optimize here a little bit this prefactor, the omega d phi. There is a little bit hidden, and we can optimize there. That's what I wanted to mention. Okay. We tried to go for in-plane field, and this is, if you had the chance to talk to Thomas Luschmann, who's working on this, this is actually a technical challenge. It's purely technical because you kind of remove any superconducting shielding from this device, which protects it against environmental fluctuation of the magnetic field, and operate it in open space in our situation. And there's a lot of kind of, sweat and pain going into the keeping this device stable and keeping the resonance frequency where they are. So this is one of the challenges. The other technical challenges which you might ask is Yeah, this SQUIDs, this limits the power handling capabilities of these microwave resonators. This is indeed the case. But I want to convince you at the end that this is actually not too big of a roadblock. It's basically just scaled in microwave power that you use for your drives. And it's still fine and doable, and you can see all the relevant effects which you know from your linearized version of your optomechanics. Keep in mind, we now are in the situation that we have a tuning field which is out of plane and an in-plane external magnetic field which is of larger strength in order to boost this coupling. Therefore, we are also looking at different modes here, the out-of-plane modes of these mechanics. Okay, so this data is, I think, a week or two old, so it's very preliminary. I just wanted to share with you what you can actually do. And for this, one kind of thing what you want to do is to demonstrate electromechanically induced transparency, because this is a step in the direction of storing information in the mechanics and retrieving it again. And it allows you to calibrate again this optomechanical coupling constant. So what you do here is you have your drive on. This drive, as we discussed, gives you an anti-Stokes field. And what you now add on is you have a second microwave tone, a probe tone, which is much weaker. And this kind of checks out or probes the interference between this probe tone and this anti-Stokes field. And if you do so, you basically get scans of this sort. This is roughly on the photon level. You get the microwave resonator here, and you see a bit of a peak and one dot here, which indicates that there might be electromechanically induced transparency. You actually now zoom in more carefully, and you see that this transparency peak reaches almost unity transparency, telling you that you can indeed see this electromechanically induced transparency features. This tells you, or you can compute then that this is a coupling of G0 of 18 kilohertz already in an external field of 15 millitesla. So it's getting there. We kind of actually convince ourselves that this device is compatible with reasonable magnetic fields. The other thing that you might ask is, yeah, you should be able to do cooling of the phonons, and indeed this is also the case. Here you do the following thing. You have your tone on, you scatter into this anti-Stokes field, which you position with being on resonance with your microwave cavity. And then that means that you prefer a scattering into the where you annihilate phonons. So each phonon which basically comes out of this cavity took a phonon away from this mechanics. So you crank up this tone, and then cooling should occur, and this manifests itself in this noise spectroscopy data where you have this sharp kind of pronounced peak which is getting broader, indicating that you get cooling, that you get an additional damping due to optomechanics, and it's getting really actually broad here that you can barely see this the hump or the resonance feature of the mechanics any longer. You can analyze this in more detail and find out the phonon number, and we cool in a field of 35 millitesla with a G0 of 55 kilohertz now to a phonon value of roughly 6.1 phonons. So this is actually dramatic, in particular because of the low power handlings. And presently, so we have to stop here due to technical challenges with our microwave resonator. However, what you can basically extrapolate is if the device would perform a little bit better here, we would reach quantum cooperativity or the ability to cool this mechanical state to the ground state at around 1 microwave photon, or a coherent time with a microwave photon. So with this, I want to flash my summary. So I hope I could convince you that inductive electromechanical coupling is actually a way forward. We see large coupling rates, and now basically the fun starts, because these devices are evidently fully compatible with kind of low-level microwave quantum signals, and we are looking forward for a bright future here. So I'm looking forward for your questions.
Okay, Hans, thanks very much for a fantastic talk. I'm sure there's going to be a few questions. So Friedemann, I pass over to you to pick a couple.
We do have a couple of questions. So maybe we start with one from the Menti. The longitudinal and vertical modes seem to have very different Q, presumably limited by clamping losses. Why do the clamping losses give different Qs for the two modes?
So this is a nice question. Keep in mind, so I try to convey the picture that this is a one-dimensional string. And this is evidently not the case, because then the out-of-plane mode and the in-plane mode would have the same mechanical frequency. So what you can actually see from these frequency differences, and you can compute it, is that the string is basically more a rectangular bar which is under high stress, and that means that the dissipation is different for the out-of-plane, also different for the out-of-plane and for the in-plane mode. So this is what is behind there. I hope that answers your question.
Okay. Maybe we move on to another one, which is how would you have to change your setup in order to see second order coupling effects?
So we don't actually. So that's what we are working on. We are trying to figure out how to access this second order coupling effects. So the second order coupling should be visible in form of a frequency shift, but the challenge is that you also expect a frequency shift due to the first order coupling. And so it's basically a conceptual challenge to find a right operational point with all the frequencies to figure out if we can quantify this second order coupling. In principle, you would say that this is best at the maximum, because there the first order coupling should vanish. But what you basically figure out is that you will need to measure the coupling as function of the entire curvature, and then try to get a full picture to disentangle first and second order coupling.
Okay.
Okay, so I'm sure there are many more questions also for Hans and for Amir. But right now, I think we're at the end of our session, or the end of this part of the session. We have a break now until the next two talks. So if you would like to get in touch with Amir and Hans, maybe ask your other questions and also just chat generally, that's going to be in, I think,